You know, there's a word in math that can make a lot of us just tense up. Logarithms. But what if I told you they're not some scary monster? What if they're actually a super powerful language for understanding the world around us? Seriously, you see them everywhere. Physics, chemistry, finance. And today, we're going to make them click, for real.
Okay, let's start with something we all know, something comfortable. 2 to the power 3 is 8. You take a 2, you multiply it by itself 3 times, and bam, you get 8. Super simple, right? We're all on the same page.
But what if we flip that question around? Instead of asking for the final number, what if we ask for the power? So 2 to the power of what gets you to 32? That question, that simple little flip, is the entire reason logarithms exist. They were invented to answer one thing. What's the exponent?
So to ask that question, what's the power, we need a new way of writing it down. You can think of it like we're learning a new language, one that's designed specifically to talk about exponents.
And this slide right here is absolutely key. These are just 2 ways of saying the exact same thing. On the left, you've got the familiar exponential form. 2 to the power of 3 is 8. But on the right, in logarithmic form, we ask, hey, starting with a base of 2, what power gets me to 8? And of course, the answer is 3. See how the base stays the base, but the answer to the log is the exponent? The exponent finally gets to be the star of the show.
Now, any good language has rules, right? Grammar, syntax. Well, logs are no different. But instead of just giving you a boring list to memorize, we're going to figure them out by, well, trying to break stuff. It's way more fun.
So let's get a little mischievous here. What if we try to ask something like log base 1 of 7, which is just asking 1 to what power gives you 7? Or what about log base 2 of negative 16? Is that even possible? Just take a second and think about it. And yeah, the answer is no way. It's impossible. You can raise 1 to any power you want, you're always just going to get 1, never 7. And you can't raise a positive number like 2 to any real power and get a negative result. But here's the cool part. These aren't failures. These broken attempts are exactly how we build our rulebook.
But what about a negative base? Now this is where it gets really interesting. Because check this out. Negative 2 to the power of 6 is positive 64. So that one works. But there's no real power you can raise negative 2 to that gives you positive 32. So it works sometimes, but not other times. And let me tell you, in mathematics, sometimes is a huge problem.
And this gets to a core pillar of all of mathematics. A rule has to be true 100% of the time, every single time. If you can find just one single instance where it breaks, well, then it's not a rule. That inconsistency we just saw, it's a total deal breaker. We need a system we can rely on, always.
And so all of our poking and prodding has given us our official rulebook, just 3 simple unbreakable rules. For any logarithm, log base a of x, the number you're taking the log of, x, has to be positive. The base number a also has to be positive. And finally, that base a can't be 1. These 3 laws make sure that our language of logs is solid and consistent every single time. Okay, now that we know the rules of the game, we can get to the really fun part, the superpowers. This is where we get to see how logarithms take these big, hairy, complicated calculations and just make them shockingly simple. I absolutely love this analogy. Just imagine an exponent, right? It's like this heavy burden sitting way up high on a number's shoulders. And what the logarithm does is it lets you take that heavy burden and just bring it right down to ground level, where it's so much easier to handle. Let's actually watch it happen. We start with log base 2 of 2 to the 5th power. Now we use our superpower. We grab that exponent, that burden, the 5, and we just slide it down to the front. Now we have 5 times log base 2 of 2. And what's log base 2 of 2? Well, it's just asking 2 to what power gives you 2? That's 1. So we have 5 times 1, which is just 5. How cool is that?
And this superpower, this ability to simplify things, it doesn't just stop with exponents. Logarithms are like a demotion machine for difficult math. A tricky power problem gets knocked down to simple multiplication. Multiplication gets knocked down to addition. And division? That gets knocked down to easy-peasy subtraction. It's literally a tool for making hard math easy.
Okay, so this is all great for math class, but what about, the real world? Well, it turns out that one of the most important logarithms of all is tied directly to a very special number that basically runs the show when it comes to growth in nature. I mean, think about it. How does a plant grow? Or how did you grow as a kid? Does it happen in these big, sudden jumps overnight? Or is it this smooth, continuous process happening every second, every millisecond, in tiny little increments you can't even see? Right? It's continuous. And it turns out there is a magical number in mathematics that is the fundamental constant for exactly this kind of natural, continuous growth. It's called E, and it's about 2.718. This number is everywhere, from how populations grow to how radioactive materials decay. It's nature's favorite number. So if E is the natural base for all this growth, it makes total sense that we'd have a special logarithm just for it. And we do. It's called the natural logarithm, and we write it as ln. So whenever you see ln, it's just a shorthand for log base E. It's the language we use to talk about all of these natural processes. Okay, it is time for the grand finale. We're going to take all of these rules, all of these superpowers that we've learned, and we're going to put them to the test. We're going to see how we can take a big, long, messy expression and just fold it up into one neat, tidy package. All right, look at this thing. Let's use our rules, but in reverse. First, we take those numbers out front and send them back up to be burdens, back to being exponents. So now we've got log of x squared plus log of y minus log of z to the 7th. Okay, now we know adding logs is the same as multiplying their insides, and subtracting logs is the same as dividing. So we can just smush them all together. And just like that, that whole messy thing is now one single elegant term.
And that, right there, is the real magic of logarithms. They're more than just a tool for math class. They're a new way to see things, a way to turn complicated problems into simple ones, just by changing your perspective. It really makes you wonder, doesn't it? If a simple change in language can make math this much clearer, what other complicated things in our lives are we just looking at the wrong way?